Hi, welcome to class. Any questions from previous material? Are there any questions from any of the previous material up to now? Yes.
I'm a little curious why, or how we were using the ground on the last Thevenin equivalent circuit. So I know we made a ground right under our.
So from this circuit?
Yeah, I believe we used that. Or, yeah.
Okay. So the question is, how do you determine where ground is in your circuit?
Or just why were we able to ground?
Or why we were able to ground it? Okay.
We didn't do it when we were using our, when we kept the resistors parallel with the ground that made them in series.
Okay. All right. So one question is about like finding equivalent resistances and why we don't have ground in an equivalent resistance circuit. So something like this. And the answer to that question is that for equivalent resistances, we are looking for a pathway between A to B. So ground doesn't matter in that case. So don't need ground. Because your pathway is from A to B. So even if there's a ground in there, you're just going to go right by it to get to B. When you're finding a voltage, though, you need to know where you're measuring from. You need a 0 point to say from that point to this point is 10 volts, or from this point to this point is 5 volts. So that ground reference is why we need to put a ground in a circuit. And so we did that on the bottom because I said I like to have things on the bottom. They look nice to me. You want to put a ground at an extraordinary node. And typically you want to put it at an extraordinary node with the most branches off it. So if you're putting it on the extraordinary node that has the most branches on it, you would have the option, there's 3 branches on the top node of extraordinary node and there's 3 on the bottom. I like mine visually on the bottom, so I picked it on the bottom. Yes? Huh? Was there another question? Yes.
I was wondering if there's like an extraordinary node on the top that's next to like the positive side of the battery or the source, and that happened to be the one with the most branches. Would you suggest we put the ground on that, even though it's on the positive side of the circuit?
Again, that goes into preference. I again like the bottom, so I'd probably put it on the bottom still because visually that looks better to me. It is going to add another unknown at that top if there was 4 branches off that instead. So I would debate, like, is that going to make sense? Maybe it is better to put it there and compare everything. Or redraw the circuit with that on the bottom and everything else around it. It would be a trade-off. There's no right or wrong answer for either of those. It's more preference of what you like. Yes?
So does the ground, like where the ground attaches, does that mean the voltage is 0 there?
Correct.
Like what would the ground be?
Yep. So wherever you put ground, that is going to be your 0 value. So that would be 0 volts from there.
Okay, so you wouldn't want to put it on the top of that resistance, right?
I mean, you could, but that's 0, and then it looks weird to have a plus 10 on the bottom of that, visually to me. So that's why I put it on the bottom. So now, like when I measure between this battery and this point, hopefully with that 20, or the 0 volts, that's easy to say that wire there is going to be 20 volts. If I don't have 0 there, it's not clear. All right, other questions? right, so we're gonna move today into, I'm gonna explain, there's also another type of equivalence called, um, called Norton equivalence. So I'm gonna ask you for the exam, they're gonna be focused on asking for a Thevenin equivalence, so do make sure you know Thevenins. But it's nice to know, like, there might be an alternate way of doing it instead of Thevenin. So you can convert the Thevenin after you've done it so that you have a current source and a resistance. How you would do that is that we want to have, if we put like an RL here, we want the same currents going through each of these. And we want to measure between here and here the same voltage. So to convert these to be the same IL, I can't write IL, I guess. IL, there we go. And the same, I should say VL instead of VTH. VL value here and here. Here you see the IL is going to be VTH over RTH plus RL. And so here we want the same. In order for IL to be VTH over RTH plus RL, how do we make that happen? It's hard to see, so I'm going to try and make it easier by removing these. And if these were open, IN, well here, and if I shorted these, I think this might be easiest to see. So if I short these, then I can see the IL will be IN. And here it's going to be VTH over RTH. So if we set IN to be VTH over RTH, then we're like, okay, those are the same. That current in IL is VTH over RTH because it equals IN. And here, this current would be the same, VTH over RTH. So this is one way to convert it, is just say IN is VTH over RTH. And then if we look at just the pathways again, and to look at the pathway, that means that we would take out the sources. And the equivalence where they're the same pathway, this would be a short. Then this is going to be the same when RN is what value? Sorry, open this up too. When it's what? So between A and B and between A and B, how do you make those the same? RN needs to equal what? What's the pathway here? Our equivalent is just RTH. So over here, RN needs to equal what? Correct? So with that being RTH, this is the only thing you need to do. So it's just another form of that equivalent resistance, and IN is just VTH over RTH, and RN is just equal to the RTH. And that makes them equivalent to each other. So when you put the load on, now that IL will be the same out of both.
So you take the RL out of it then? Or is the RL still?
So the RL, yeah, you take it out, and so it's only gonna look at the VTH and the RTH. So the VTH can be determined by the Thevenin that we did last time. The RTH is, again, can be found that way, and then if you want the Norton form of it, you can just convert it over to this one where you have the IN and the RN with those values. Yes.
For the one on the left, if you're shorting it across the R and the load, why is the current formula still the R load in it? Why is it VTH over RTH plus R?
Oh, I see. So this is for that circuit when it is connected. So let me redraw it. So when I do put on the load, so that was just because of this circuit. So those were separate. Sorry.
Is there an advantage to using one method over the other?
I never use Norton, to be honest. I like the Thevenin, and so I usually always do the Thevenin. So it's more preference, and then there is a case where it's easier to see if I already know what IN is. You don't have to take then I'm looking more for the currents. Most of the applications I always work with were usually the voltages, so that would be the only other time. All right, any other, yes?
What we need to know both for the exam.
No, Thevenin. But be aware of this because you may see it at other times. So, all right, any other questions? Okay, so we're gonna skip finding it because as I said, I don't require you to do that with the exam. Okay, so going back to the RoboBee. So how do RoboBees communicate? If any of you have seen bees, they do communicate. They will go in big groups to sometimes. They actually communicate. I don't know how they communicate, but they do communicate and let the hive know, like, oh, there's a new flower. And so they all go to the new flower. So there's some ways that they are communicating with each other. So that would be something else we may want to think about with the RoboBees is like, how are they going to communicate? So one way of communication is to use what's called an antenna. There are different types of antennas. Dipole kind, loop kinds, helix, different shapes of them. And then you can make them on these really small chips and actually make antenna chips or antennas on the small chip itself. So all of them require power though. So they do require enough power to be able to send out the signal from the antenna and receive the information from another antenna. So we need to do what is called maximizing the power being delivered to a load. In our case, this would be kind of like an antenna would be our load. It could be modeled as a resistor. It would look like this. So we have our more complicated circuitry that we've now modeled. Say the circuitry is actually the circuitry that's preparing the signal to be sent on the antenna, or it's the information when it comes back. The load on that one would be an antenna to receive the signal and then all of the electronics to interpret the signal. So those are being modeled right there. That whole system is in these three simple components that you now know how to analyze. So finding the RTH and VTH is more complicated when you have like a microcontroller in there, but it still has some components that we can model it with resistors, voltage sources, and then we also have two more components that we're going to learn about in some other units. But for now, since this is all you know, how do we actually get that maximum power delivered to the load? So we want to deliver out maximum power. Because we want the most information that can be sent through that antenna so that they're communicating correctly. So, anybody remember when you have signals? Well, let me go back to a graph. Okay, so back to math. How did we find the maximum of, say, a signal that looks like this? Anybody remember? Okay, so the slope is 0. So how do you determine that that slope is 0? Okay, so I'll call this x and y. So we would take dx dy and set it equal to 0. So we're going to use that same concept, and now we have we're on 6, maybe. Sorry, material such So I here is going to be what? What is it? Okay. So voltage divided by resistance. Thank you. So we have RTH RL, and then we also know the voltage here is going to be what? So to find voltage, what do we need? We need to know 1 point on our graph, 0 volts. So that's always going to be what I'm going to return to now. Hopefully it will get some in. So where are we going to put it here? Where do we want to put 0 volts? Should I put it here? I don't want to put it there. That looks ugly. Thank you. Okay, 0 volts. Okay, with 0 volts, I know that when I compare now and find the value here, that will be 0 volts. Or I mean, that will be my VL. So I noticed, hopefully you noticed, that it's the voltage across that RL. So what is that going to be? I heard somebody say it, voltage divider, correct. Okay, so voltage divider, the voltage applied across what resistor? Correct, RL. And then over the summation of all the resistors. So now our power, I'll put VL for the voltage, the load. I times VL is going to be VTH squared RL RTH plus RL squared. So the same idea is to deliver the maximum, we need to know RL and RTH, or we know RTH values. We need to know what that load value would be. So we're going to take that same concept, take the derivative. So I'm going to take the equation. And now we're going to take the derivative over, maybe. There we go. with respect to the RL. So if we take this function and take the derivative of that with respect to RL and set it equal to 0, that can give us the value for RL that will give us that maximum. So VTH squared is going to be a constant, so I can bring that out. And then there's a 0 on the other side, so if I divide that to the other side, that is going to go away to 0. So if I divide that here, VTH squared, that hopefully is easy to, yes, it goes to 0. So then I have to use, because I have RL on the top and I have RL on the bottom, so I have to take the derivative of the first, multiply it by the bottom. So I could rewrite this as RL times RTH plus RL to the -2. So do you guys remember this, where you have two variables, you have to take the first, is that called the chain rule? I can't remember if they call it, whatever they call it now. Anybody know what they call it? Is this still the chain rule? Okay. So you have the derivative of the first, which will be 1 times the second. And then you leave the first one and take the derivative of the second one, which becomes in -2, and then a 1 from inside, so RTH plus RL squared, -2 squared, or -3 minus 1. And then combining these to get a common denominator of RTH plus RL cubed, I have to add a term from this first term, and then a -2RL. So multiplying this over, I get 0 times that, so that goes to 0. So this becomes RTH minus 2RL equals 0. Oh wait, I missed the plus RL. RTH plus RL minus 2RL equals 0. So RTH then becomes RL. So that's when my maximum power is just I set RTH equal to RL. So now you don't have to go through this derivation every time, you know, like, well, I've already seen this derived. To find the maximum power, all I have to do is say that R load has to be equal or as close to possible as that RL. RL needs to be as close as possible to that RTH value. Yes?
At the very top of your purple writing, could you kind of just infer that if you were to plug in 0 for either RL or RTH, that one would equal the other?
Yep. Yeah. You don't have to go through the math algebra. So yeah, just when it's going to be equal 0. So if you're looking at, you know, we usually do that when we're looking at roots and when are they going to be 0. So here you could say the term on the bottom, RTH plus RL, is only going to be 0 if they equal each other. All right, other questions? I don't see that though, so I have to go through the algebra. So. All right, so this is going to give us our maximum load. So let's go through an example. Okay, I'm just skipping through these. Okay, so we want to first find the Thevenin because we have to find the Thevenin before we can find the maximum power. So for this, our RL is going to be here. So you're going to take that out, put A to B there, and find the Thevenin. for this circuit. So I'm going to make this easier to see by just fully removing that. Okay, so go ahead and try to find the RTH, the VTH. If you haven't met your neighbor, meet your neighbor and work together with them.
R1 and R2, like R3 and R3 is was thinking about that. Okay, no, I did it right.
Okay, so there's two different ways of solving this. Either method is going to be fine. You do, so first off, highlighting. So I'm going to highlight the nodes. I'm going to start with finding RTH. So with RTH, I'm going to remove the sources. So when I remove the sources, what do I do with the 9 volt? Correct, wire. So that becomes a wire here. And when I remove the current source, what happens? It breaks or just an open. So it would look like that. And then I'm going to find the pathway between A to B. So when I take the pathway, I start at A. And I notice that it splits here. So I have two different paths, which means it's going to be parallel. Whatever's in one branch is going to be in parallel with the other one. I notice here that I have this branch and I have these elements in this branch. And so it's going to be those two in parallel to each other. So the RTH is going to be 40 in parallel with these two in series. So 40 in parallel with 360. So 1 over 40 plus 1 over 360. And what's that end up being? 36, there we go, 36 ohms. Okay, so kind of a summary of the steps is to remove the load always though. So you're going to remove the load. So physically redraw the circuit and then go from there. So to find VTH, you have two options. You can leave the circuit as is, or notice that there's two sources and you could use superposition. So I'll go through both ways of solving it. So going through it first with superposition. As I do superposition, you're going to take out one source, leave the other. So in this case, removing the current source and leaving the voltage source. So you're left with this circuit. Again, I'll highlight them. So highlighting the nodes. All right, and then also labeling, are they ordinary or extraordinary? So this one is going to be, so the blue one is ordinary or extraordinary? Ordinary. And I did this the same color because I knew that. So both of those are ordinary. This one is extraordinary. So that is also the exception. When you're finding VTH or RTH, is that you know because you removed the load, there's going to be something connected there. So that makes that node extraordinary instead of just normally what is ordinary. And down here, this is also going to be extraordinary. So now I need to know the voltage between this top A and B. Again, I like the bottom, so I'm going to label that 0 volts. So now that I have that 0 volts there, I know I have to find the voltage. I know the 9 volt. I would have to find the voltage across R1 in order to find that voltage, or it would be the voltage across R3 and R2. So I see that there's different pathways here. So this is one pathway to get from A to B, and this is one pathway to get from A to B. So I also notice that it is one current because one branch. So these are dangling, so there's no currents differently going there. So I have just one current, and I have a whole bunch of resistors, and I know voltage. What can I use? I can use a voltage divider. So I note with the voltage divider that again, that pathway without the source in there is between those two resistances. So I have to combine them in order to find the voltage across both of them. So this would be a combination of R2 plus R3. And then I would do the summation of all of them. So this was 120. This one was 240. And this one was 40. So 360 over 360 plus 40. Which gives 8.1 volts. So the next part of this would be to eliminate the voltage source and leave the current source. So removing the voltage source gives me a wire there. I used red, so. Green and blue. Okay, so highlighting these, again, what is the red? Extraordinary, ordinary? Extra, correct. Again, I'm just going to label this for now. Green. It looks ordinary, but remember, it's extraordinary. Lou? Extraordinary. Okay. Current that looks like there's 2 branches. Even though this is extraordinary, there's no current flow that's going to go in that wire. So the same current is going to go in each of those. So looking at that, I have one current in between R1 and R2. I have a different current that's going to go through here, but there's only resistors in there. What can I use here? Not voltage divider. Current divider, yes. Current divider, correct. So you could use a current divider. So we want to find what current? So again, the pathways are, I could go from that node to here, find the voltage across the R1 there, if I knew the current. Or I would have to find the voltages across both those resistors there. So it'd be easier probably to find I12 and take the resistor value and multiply those together. So I'm going to go this pathway, which means I need to find this current. So that current is going to be what? Is it positive or negative is the first question.
Positive.
Correct. So it's going to be positive. It goes into that node, and then it flows down the other 2. So this one, though, should be going in this way in order to be positive. Okay? So just note that. So yeah, plus 50 milliamps. And then you can either do 1 over R1 plus R2 over 1 over R1 plus R2 plus 1 over R3, or 50 milli times R3 over R1 plus R2 plus R3. They should be the same. Again, these are 40 ohms, 120 ohms, and 240 ohms. So this gives a value of I12 as 30 milli. So now VTH, called the dot I, is going to be a plus or a minus of I12 times R1. So this polarity is plus on the top, minus. What is the polarity on the resistor? On the left side of it is going to be what? Plus, minus. Are these the same or are they opposite? So what polarities are on the same colored wires? Okay, so to determine if they're the same or the opposite, it's whatever's on the wire polarity. So you can see on the green, there's a negative on that from the R1, and there's a plus on it from the VTH. That would be opposite. So if you visually don't see it, make sure you're looking at the polarity that it has on the wire. So these are actually opposites, and then on the red, that's a plus and that's a minus. They're opposite. So this is going to be a negative I12 R1. So this gives negative 30 milli times 40 for a value of negative 120 or 1.2. 1.2 volts. So to find the actual value, you sum these. And the first one we had was 8.1 volts minus 1.2. And that gives us 6.9 volts. So this is our end value for the VTH. Okay, any questions on these steps? So going back to review, so found RTH, one, removed the load, and then found the pathway between A to B. To do that, also had to remove the sources. Voltage source became a wire, current source became an open, found that pathway from A to B. In this case, we saw that it had A and then it went to two different branches. So it was the first branch in parallel with the second. In this case, 40 in parallel with 120 plus 240. And that resulted in 36 ohms. Next step was to find the voltage. So did that using superposition. In superposition, then I had to find voltage, you want to zero reference point. So you had to put in the ground. So we added in the ground. And then from there, I noticed it was a voltage divider when I removed the current source. So the voltage divider was across the R2, R3 there. Then I redrew the circuit with the current source and removed the voltage source, and that gave me this circuit. Again, I put in a ground because I need to have a reference point to get to whatever voltage I'm finding. So that gave me the 0 volt on the negative side of where I was trying to find it. This ended up being a current divider, so I used the current divider equation. And then I summed those two results to get to the end value. Yes?
You're finding I12, why'd you decide to use the R3 on your current divider, like 50 milliamps times R3? Is that just because it was in parallel?
So you have the two branches, and if you're going to use the one that's not the conductance, so this one is called the conductance one. So the conductance is going to be the same resistors in the branch you're trying to find. And then if you're not going to use that, you have to use the opposite branch resistance. In this case, that opposite branch resistance was the R3. So this is the opposite branch.
If you do the opposite branch, then on the bottom you don't have to do the like when you're summing them, you don't have to do the parallel thing.
Correct.
You can just add them all. Okay.
Yep. You can just add them all as long as you only have the two branches.
Right.
So this was why I would, if I had more branches, say I actually had something that was another one that came off, then I would have 3 branches. I could use the conductance form. I have to combine R1 and R2 for one branch combination, and then I would use, plus R1 over R4. I could do it this way and add that one in there. Otherwise, my opposite branch in that case would be R3 in parallel with R4. And I would have to combine those first in order to be able to do the current divider.
Okay.
All right, other questions? Yes.
For I12, when we're doing conductance, why do you do 1 over R1 plus R2? Why is it not 1 over R1 plus 1 over?
So kind of that same thought, you have just 2 branches, so the branch resistance is what you're doing the summations over. So this is the branch resistors. So summing up the branch resistors. So in the case where I12 is, the resistance in that branch is those two in series. So you have to add them together. So that's the R equivalent of that branch resistance.
Okay, but why are you doing a 1 over that?
The conductance is just 1 over.
Okay.
Does that make sense? So you have to first combine them as a resistance in the branch, and then you take 1 over each branch resistance. All right, other questions? Yes.
So in the first part of the superposition, when you took out the current source,
Uh-huh.
when you did a voltage divider, why did you choose to do like the second and third resistors together rather than do the first one over the total?
So the first one is only going to give me the voltage across this element. So it's only gonna, if I did a divider there, it would only give me the resistance between, across R1,
Oh, okay.
which doesn't give me the value of VTH dot V. It only gives you the voltage across that one resistance. So I could find it there, but then that's only there, and I would have to take 9 minus that to get to VTHV.
I see.
Does that make sense?
Yeah.
Okay, so that's why instead I just combined R2, R3 together and found the voltage across them together. I felt that was gonna be easier. Okay, so if I don't see these are voltage dividers, current dividers, I don't wanna use superposition, then you could go back to our other techniques. So, I'm gonna go here. So I would still find RTH the same way, so that's not going to change. What's going to change is I'm just going to leave the elements in there. And this time I'm going to just take I'm going to use KVL, KCL, and Ohm's law. So I'm going to highlight these again, red, green, and so this is red. Green and blue. And this is an ordinary node there. Okay, so highlighting them, identifying what kind of a node are they. So this one again will be ordinary. This one is extraordinary, this one's extraordinary, and this one is extraordinary. I'm going to put a ground, and then my VTH is going to be that plus to minus. So here, again, I can find the voltage across R1, and then use the 9 volt to get to that value. Or I can find the voltage across this one and this one, which is going to give me the pathway here. So either way, I can find that voltage. I'm going to arbitrarily pick one of those. And I think I'm going to do this one. So in order to do this, I'm going to need to know the voltage across this one and the voltage across this one. So I'll call it VR2, VR3. So from ground, I'm going to go in this direction, plus, plus, and then a minus. I'll just rewrite my whole equation. So plus VR3 plus VR2 minus VTH equals 0. And now I need to know VR2 and VR3. So I'm gonna label a current. I'll call it I1, 2 again. It's gonna be the same current that flows through this one. I'm putting it in the same direction that I labeled the polarity there already. Is this current here VR or I12? Now it's not, right? So now I'm gonna call that some other variable, I3. So I have I12 unknown and I3 unknown. With labeling those, I can say these are the same polarity. So I3, R3, and then VR2 is going to be I12, VR2, oops, sorry, R2. There we go. And now I can do KVL, KCL. This is my Ohm's law. So this is going back, this is Ohm's law. And now I can do a KCL. So doing a KCL there, I have I12 in, I3 and IS out. And then my last option is a KVL. And so I'm going to do the same loop, but I'm going to continue it around. Instead of going here, I'm going to go all the way around and back around. So that's going to give me a plus here, and then this is a plus to minus and a minus there. So plus, and I'm just going to substitute this in, IR3, R3, plus I12, R2, plus I12, R1, minus 9 equals 0. And I have one equation here and two equations with the two unknowns. So I can then algebraically solve this and get the same answer that I got before. So this should yield that VTH is equal to 6.9? What was it? 6.9 volts. All right, questions? So two different methods, they would yield the same answer. So good ways to say I'm going to solve it one way and then go back and check another way. All right, questions? Any questions? Okay, so now that I have this, I have a 6.9 volts. Copy the screen again. There we go. Okay, so this more complicated circuit and I can represent this whole circuit by those two elements that I just found. So 6.9 volts, and then the resistance I think this was 36 ohms if I remember right. 36 ohms. So now I can calculate the current going to this load. I can calculate the voltage across this load and find power delivered to the load too. So I is just 6.9 divided by 36 plus 72. VL is a voltage division across the 72, if I ground that. So 72 plus 36. And then I can find the power to the load. Yes,
Where did the 72 ohms come from?
that was given as the load.
Oh,
So that came in for this particular example, it was given as a load.
okay.
Is this going to deliver the maximum power? Is that load going to be able to draw enough power to give you the maximum? I'm seeing no. No is correct. Why? What would you have to do to the resistor to get maximum power? The load resistor. We would need to lower it. The closer it got to 36 ohms, the more power we're going to get. And that's going to give us the most at 36 ohms. So changing this, so I'm going to quickly calculate this. So 6.9 times 72 divided by the 72 plus 36 gives me 4.6 volts. The current gives me 6.9 divided by 36 plus 72. So this gives me 0.064 amps. So the power here gives me 0.064 times 4.6. Uh, 0.294 watts. If I change that to 36, then the max power it's going to change to, I could even just go back. Get this one. So I had already calculated this one. So this was the max power equation, so I could use that, or I can calculate it by just going back, finding I for this one and VL for this particular one for 36. I'm gonna do this in a different color. Ohms. So this gives 1.3225. So you can see, yes, that's a lot bigger.
How come RTH plus RL is 36? Where did RTH go in the Pmax equation?
Sorry. Times 2. Sorry, just forgot to write the 2 in there. Yeah, it'd be, I'll rewrite it. It's hard to read that. 36 plus 36 squared. Oh wait, did I? So no, I actually calculated this one wrong. Sorry. So 0.33. So not quite as big, but still larger. All right, questions?
How are you able to replace all the resistors with just one 36 ohm resistor if they were on like either side of the A and B? Or if they were on like either side of where A went in, if that makes sense.
So we accounted for those in the pathways that we took. So when you go down here. So this is the equivalent that you're trying to get to. And the method that we used was like, okay, we remove this one, we short or put to zero every source that's in the circuitry, and we find just the pathway between here to here, and that gives us RTH.
Oh,
We're
okay.
doing the same thing for the complicated circuit to find that pathway.
Even though we only like we did one side of it to find RTH, because remember you said there was like two sides that you could try, right?
So we did go through both pathways for the RTH. So in the RTH, we did account for both pathways. We accounted for the 40, and it was in parallel to the R2 plus R3, which are both pathways.
Okay. Right.
Voltage, we only did one pathway because it can be either or to get to that location.
Oh, okay.
I think that might be what was confusing there. All right, other questions? All right, you guys, make sure to do your homework and assignment by tonight, and then quiz will be open only tomorrow, so make sure to take it tomorrow. Have fun. See you guys.